Hello students, we are into chapter 3 and we are studying the transfer functions for different kind of systems. So we started with mechanical system which we know already, a spring mass damper system, and then to LCR circuit we looked at what is transfer function there, then op-amp circuit, what is transfer function there, and with op-amp circuit we also saw that we can change the transfer function. I mean, what I mean to say is, if the transfer function is given, op-amp system is such that you can achieve those transfer function. Yeah, so just by manipulating the position of resistance and capacitor and all, so based on that we can do it. Okay, so we will come back in details later on also, but now we will move to different kind of system now. Okay, so electromechanical system. Okay, so to start with, when you say electromechanical system, it will have some mechanical part such as the like a motor, for example. So from the you give a voltage input, and the output is some torque which is applied to run some load. When you say load is like flywheel, for example. This is the one load, right? Or the wheels in your car is a load, so you have to drive them. So typically what we will say, so we start with the mechanical part of the electromechanical system, and finally the function of a motor is to drive something, some load it drives, right? So say let's say flywheel. See, you have to drive a flywheel. So let's draw here. Yeah, so flywheel is like this. Yeah, so like this. Okay. Now when you say flywheel, what is the input and what is output? So always system, for any system there is a input, there is a output. Yeah, so in this case what is the input? Yeah, so input is you give some kind of a torque, right? So torque is input. Yeah, so and output is the output will be some kind of, so looking from this side, so anti-clockwise will be the positive, so we put like this one, and hence if the torque is the input, the output is maybe two things. Either it will be omega. We can say, let's say start with omega. Omega is the angular velocity basically, right? So this is input, this is output, and what is the relation? Always when you are talking about the system, you also have to talk about the relationship between input and output. So this is say input and this is output. Yeah? And relation is the Newton's law of motion. From there, the second law of motion, what it says, the force will be equal to J times the M times A, where A is the V dot, right? V dot is, in this case, is omega dot, yeah, or equal to J theta double dot. Yeah, so in this case we are defining the output is omega, and hence since omega equal to theta dot, and hence we just write like this only. Why? Because the output in this case, if our output is just velocity, angular velocity, then this is the which is valid. So this torque is a function of t, and this omega is also a function of t, right? So yeah, so take the Laplace transform of this one, and finally what we get? We get this torque. Let's call it something else. So maybe we call it moment. So that way we are not confused with and say mt like this one. So this is a moment. Yeah, say moment. Yeah, okay. And so we have here the moment which is a function of t is equal to like this one, and finally if we take the Laplace transform, this will be ms equal to j, and this will be big omega, and then we have s here, but dot, so we have multiplied by s like this one, right? So basically the output over input or transfer function, this is a transfer function. Transfer function in this case will be equal to, the output is omega s, so omega s over ms, which is the input moment, right? Moment, or equal to torque. Basically this is what, this is torque, yeah, okay. So this will be equal to, you have j times s, sorry, 1 over js, 1 over js. You get simply like this, okay. Okay, so here this one is the moment or the torque we are applying, this one, this is the output, the angular velocity we are applying, and then this is equal to 1 over js is the simply is the transfer function. Okay, it's possible that when you are applying here, there may be some bearing or something, right? So always like in motors we have like that. So if the bearing is there, then equation will be different. There will be some friction also involved, right? So friction. There will be some air friction also because of the when the flywheel runs, and then there may be some air friction as well. So we can also write the torque. Basically this m is little bit so maybe we write tau, so tau is better, yeah, okay. So accordingly we can change it, make it tau here, tau, yeah, let it be tau only, tau like this one is here, and then this will be tau, yes, yeah. So tau is the torque or moment, yeah. So this is the, yeah, this is better. This is tau is a torque, and this is the omega is the output velocity. Okay. Now next is if there is a friction here, then we can write the equation will be tau t is equal to j omega dot plus maybe some C kind of thing will come into picture, right? So damping, right? So write B omega, okay, where B is equivalent to damping, yeah, damping coefficient for the rotational system, yeah, it's not linear system. This is equivalent to C basically, right? So this is velocity, so this will be how it will be, yeah. So you are used to j omega dot plus basically this is something like j theta double dot plus b theta dot equal to tau t, right? So this equivalent to m x double dot plus c x dot is equal to tau t, something like that, yeah. So this kind of system is equal to f. This is equivalent to like this one. It is something like you have just a damper and a mass here m, and applying a force f t. So this is what the equivalent of that will be, right? So same equation. So for this equation, the equation looks like this one. Take the Laplace transform of that, and what do you get? You get tau s is equal to j s omega s plus b omega s, and hence omega s over tau s, which is a transfer function, will be equal to, so omega s over tau s will be equal to 1 over js plus b. So in this case the transfer function will be like that, yeah. Okay, so in your quiz or continuous assessment, I can ask that question, say if the output is angular velocity, input is torque, if there is a friction also there, okay, so in that case what will be the transfer function, so given some values, or that question may be in any form, but if there is a friction, then the form will be like this one. This is without friction is this one, this is with friction. Yeah. Okay. Now this is where your input is torque and output is omega. Then, but sometimes the output could be, you are measuring in terms of theta as well. Yeah. So in that case, what will be the transfer function? So equation in that case will be different. If the output, output is theta, then this equation becomes the tau t is equal to j theta double dot, right? Simply, instead of the omega dot, you have theta double dot, and hence apply the Laplace transform, you get tau s is equal to j s square theta s, right? And hence you will get the Ts will be equal to, which will be equal to theta s over tau s will be 1 over js square. Okay, so this is with without friction. Okay, and with friction, this is without friction. Okay, now with friction, okay, so which kind of friction? Here it is a damping friction basically. Yeah, so here whatever we are doing in this case viscous friction. Yeah, so with I would say right here viscous friction. Yeah, so without any friction, with viscous friction here. Okay, so in this case equation will be tau t is equal to j theta double dot plus b theta dot, and hence you apply Laplace transform and we get tau s is equal to js square plus bs, and then multiplied by theta s, and hence transfer function becomes 1 over js square plus bs. Yeah. So this is what you get. Okay, so I may ask question something like the output is the angular displacement rather than angular velocity, and in that case what is the transfer function? Okay, so remember this transfer function, this one is when the output is omega, that's angular velocity, and this transfer function when output is theta. Okay, for the same system, if the output is different, the transfer function will be different. Yeah. So similarly for this one, this and this are both represent the same system. However, here input remains the same, that's torque, but output is different. In output in the first case is the angular velocity. The output in the second case here, output in the second case is the angular displacement, and hence you have different transfer function. So remember that. A flywheel like this one is actually also in control theory term also known as the plant, right? The plant, okay, which you need to run. And how do you run? You run using actuator. Yeah, so this is a motor. So this is a plant, actual load basically, or in this case it is load. So it's a plant, and everything whatever you have is for this one only. Okay, so since you have to run a load, basically you have to rotate the tire, for example, the wheel. Yeah, so because of that you have the motor and what you call it actuator. So this actuator will be doing that. And motor, for that input is, there will be some input, yeah, and the input will be some voltage, some electricity, right? So you provide some electricity in terms of voltage and it is going to run. It will run and produce torque. Yeah. So if you look at just the motor, what it is going to do? You have the input voltage. Let's call it EA, like this one, and then you have and here there is a produced is what produced is torque T. T is the output and EA is the input. This is A for actuator. Okay, so the input voltage is actuator, output is the output is the torque. So here this is electromechanical system, where input is regarding electrical system quantity and output is a mechanical quantity. This is torque, right? So in the other case, when we looked at the flywheel, it is a purely mechanical system because input was torque and output was the angle. So kinematic system basically, right? So it's a mechanical system. This is the real electromechanical system, where you have electrical input, mechanical output. Now there are some details we have to find out. This is a black box right now, so we have to find out, since this electrical system, we have to find out how the electrical circuit is inside the motor, that we have to know. Second thing is how torque depends on some quantity inside it. Okay, so relationship. So first relationship is will be the motor itself, right? So inside the motor, what kind of things are there? Remember that when motor runs, you have to also see the principle how it works, right? So typically what is there? There is a magnet. Inside that there will be the coil, right? And you connect it to electricity, and because of that some force will be generated, yeah, and because of that it will start running, yeah. So when it runs, that really means the system inside the motor will have something like this. Few things. There will be a inductor, which is because of the coil. Then there will be some resistance. Yeah. So let's call it LA, inductance. Then the resistance RA will be there. Yeah. And then there will be okay. Back EMF is generated because this is a coil also, and when you basically the magnet is there, yeah, and it's a coil also there, and then the closed loop, if armature is rotating inside that, it is also going to produce electricity as well, like electrical generator, yeah. So there will be back EMF as well. So back EMF is also generated. Yeah, so and that will be equal to, like, this will be something like this, yeah. So this will be equal to EB, let us say, yeah. So here you have EA, and there will be a current flowing, let us say it's called IA. So there is a inductor, the resistance is there RA, and then is the back EMF is there, and that is producing a torque, right? This is producing a torque T, like this one, yeah. Okay, now how is torque related? Torque relates to IA only. So T is equal to, let's say, call it KB times IA. Yeah. So this is a constant, relates the torque. The torque, I think we have to write tau this way. So write tau. Yeah? So not to be confused, tau. So this is tau. So tau torque, yeah, is proportional to the current which is flowing inside it. Yeah, and we know from the +2 we have those topics when in a coil, when there is a current flows, then it is and if it is in a magnetic field, then it is going to turn, right? So say, I mean, it's going to face there will be some force applied to that. Yeah. So and more the current is, more the force generated, and hence the more the torque is generated, and hence the tau is proportional to Ia, where Ia is given, that the current flowing through this loop. Okay, so this is like that, or take the Laplace transform, and what you get, with tau s will be equal to kb, which is constant, and then Ias, like this. So this we have one thing, and this is about the how the electrical system, this is the electrical thing, this is the mechanical thing, how the electrical current is converted into the final torque. This is what the relationship it gives you. Yeah, so this is the gain, or this is what the you call it proportionality constant. So this we have already, let's call it 1. Now second thing is, now you have to find out this one, and what remember our input is not Ia, our input is Ea. So we are giving the voltage, and output is tau. This is just the intermediate. This is one part of the story. Here the we have to compute this one, and how we are going to write Ia in terms of Ia. So what do we get? We get La, then dIa over dt, right, plus Ra Ia, and then you have back EMF, so it will be like Eb will be equal to Ea, right? Okay. Now Eb, what is Eb? Eb is a like EMF, right, electromotive force, and Eb also has a relationship. Yeah. Now, and what is that? Where Eb is equal to, Eb depends on only the, it's a back EMF, and the magnetic field is constant for that. Yeah. So the more velocity it has, the more the electromotive EMF is generated. Yeah. So that really means Eb will be let us say we call it equal to K A times theta dot. Okay. So Eb proportional to omega, basically, right? That's what it means. So the electromotive force, which is generated by a the coil in like rotating inside a magnetic field. If it is not moving at all, there is no current. Yeah, and hence there is no electromotive force generated. It starts moving more the slow. It is moving slowly. Hence EMF will be smaller. It is faster and faster, and hence it will have more and more. Yeah, so that's why it is like this. Okay, so hence this is one thing we have, and we can do the Laplace transform of that also. Yeah, and what we will get is Eb s will be equal to Ka times theta s times s. So this is another relationship we have. Here also what you see is a relationship. This is relating the output torque with the current flowing in that. This is establishing the EMF generated because of the theta. Yeah. So since the torque and omega are related, right? So the output in this case is not only torque, but also output is the omega as well. Yeah. But here because the ultimate output is theta, right? So there is another one here, right? So we have a connected to this flywheel, and flywheel's output is theta. So the theta is ultimate output, but theta is relevant here because EMF generated will be equal to theta dot, and hence it comes like this one. Okay. Now we have this equation, so we take a Laplace transform of that, and what we get is LA, and from here we get IAS times S plus RA, and then you have IAS plus EB, right, plus EBS will be equal to EAS, right? Okay, or EBS we have in terms of EBS, we can write in terms of KA times like that. So we have LA, IA. Okay, so now let's have this only, because we have to relate with other things. Yeah, so we have that. Now we have this theta, and also we have a tau here. So from the plant, that is for the view. Yeah, so we already have, what do we have? So we already know that the output, that means theta S over tau S. Yeah, output over input is already, we have 1 over J S square plus BS. Yeah, so we have of this form already. Yeah, so since theta, we have the theta term here, theta dot term here, so here also we have to take theta as the output, and hence theta S over tau S is there. So this we have to take. So we have 4 equations, this, and the 4 equations will give something. Yeah, so we will simplify it, we will find out what we get, and that will give us the this input to the if the input is EA, output is theta, what is the relationship that will give. Okay, so we have 4 equations. As I said, this, and this one. So we can combine it. So from this and this one, what do we get? We get theta S equal to tau S. This one is KB IAS divided by JS square plus BS. So we get theta S. Now, so this and this we have combined already, right? So this is done. Next is this and this we can combine. So what do we have? Theta S. Here we have EBS, right? So we can replace, and we can find out from there EBS will be equal to KA times theta S times S, right? So KA times S times theta S, and theta S is this one. Theta S becomes KBIAS divided by JS square plus BS square. Okay. So finally, what do we have is this one. EBS equal to KAS multiplied by KB, right, multiplied by IAS divided by JS square plus BS square, and the whole thing you can put it here, right? And what we have in terms of IA and in terms of IS, right? So okay, so let me remove this one. From this equation, what do we get? We get the IA here, IAS will be in common, and we get this one, which is LAS, plus we get RA plus and EBS, where EBS equal to this, EBS IAS is common. What remains here is KA times KB, K times KB, then S divided by JS square plus BS, is the BS here, not BS square. So KA times KB times S, IAS is common here, divided by JS square plus BS. So this is what we got till here equal to EAS, right? Okay, so transfer function now from here till the end, till the theta part. This is theta here, right? So finally it gives torque, and when this is torque is there, and then torque related to theta as a plant, right? This is a plant here. So now if you want to find out the transfer function from here input to the motor, if this is input of the voltage given to the motor, and theta is the ultimate output. Let's say called the ultimate output. This is ultimate input. Okay, so transfer function in that case will be equal to okay. So we are not exactly getting that because this one is IAS. We can do that also, but from here, what we are getting from here is simply some different kind of transfer function, and that is we'll come back to the ultimate one later on. So right now, what we are going to get is if the input is IA, the EA, and output is the current. You are getting the current, and from there you can relate later on. So right now, TS in this case will be equal to EA, that is EA over. So this is output. So this is EA over EAS will be equal to, so 1 over, and you have this LAS plus RA plus KA KBS divided by JS square plus BS. So this transfer function is only for the from here to here. Yeah, this is the what gives you the if given the input voltage, what is the this current EA. So this EA output. So this one is for this part. If given this voltage, this is the output part, and hence it gives you like this one. Okay, in terms of all the system properties, this is giving you. But if you, since you know this one, other things you can find out now. So transfer function of just this one, just for the actuator, is given by TS equal to IAS over EAS, and like this one, just to find out the current. Once you know the current, others you can know automatically. Yeah, and for that we have already found out. So if you know the current, you find out the torque. So torque is equal to, as we say, this will be equal to KA. So tau S, earlier we had tau S equal to KA times IAS, right? So that's what we had, and hence if we have tau S is equal to KA multiplied by our IAS is given by this one. So we given by EAS divided by the whole thing, this one. Okay, so what do we have? We have LAS plus RA plus KA KBS divided by JS square plus BS. Okay. So this one, what it is here, your now I can remove this one. So far what relation we get? We are getting how the tau this transfer function, another transfer function, it is the this is tau S divided by EAS. Now we are talking about how the torque related to the this input voltage, and which is given by KA divided by LAS plus RA plus KA KB divided by JS square plus BS. So this is, let's call it, this is the, okay, tau s equal to, yeah, okay. So let's call this one is T1, okay. So this is the torque output divided by the input voltage, which is given by this. Yeah, okay. Now we have to find out ultimate. As I said, this ultimate input is this, ultimate output is that. And the relation is basically we have to find out theta, right? Like theta s given the torque, right? So theta s over tau s is this one, right? Okay, and here tau s is given by like this one, so will be equal to, and theta s will be equal to tau s, theta s over tau s is given like this one, and this is ultimate, I will say ultimate, is called ultimate, the transfer function t, let's call it u for ultimate, TUS will be equal to this one, so tau s over EAS, right? And then we should have theta s over tau s, right? So that you have theta s over, basically theta s over EAS, right? That's what we are wanting, right? So the tau s over ES is this one, and then this one is this is the one which is the motor, right? So what do we get here? So the final value will be equal to, we write here, equal to, so we multiply this one, so we have Ka over LAS plus RA plus Ka times KBS plus JS square plus BS multiplied by 1 over, and then you have JS square plus BS. So this is the ultimate transfer function, right? So this is TS, let's say U equal to, right? So given the input here voltage and the output here theta, so U over theta is what is the given by this one. Yeah, so this is the how we are relating the mechanical system, the electrical system to the mechanical system. Okay, so we will simplify this one. What we got so far was there is a plant here. Yeah, so it's a plant, and for that the transfer function is equal to 1 over JS square plus BS, right? Okay, and we call it plant. This is the plant. Now we will write as the flow diagram, the block diagram, and this is the, before that there is the actuator, yeah, and for actuator also there is a transfer function. And what is transfer function? We can simplify this one. So what we get here, S, you have S value here, and here also JS square. So what we will get is simply S and S cancels out here. So we get simply divided by, and we have LAS plus RA multiplied by JS plus B plus Ka times Kb, and this goes up, this is Ka times Js plus B. So this is actuator. Yeah. So since here two things combined, this one is basically the theta s divided by tau s, and this part is tau s divided by EAS, right? So torque divided by volt, input volt. Here it is theta divided by input torque. So separated. So both combined together. So here we have separated this first and then. So transfer function 1, transfer function 2, and then hence the ultimate you want from here to here. Let's call this is T1S, this is T2S, and hence the ultimate one here. What you have? You have EAS. Here you have a tau S, and here you have the theta S. Right? This is the block diagram. Plant output is theta S, input is tau S. For actuator, tau S the output, input was ES, and the whole thing is given by this multiplied by this one. So tau U S will be equal to T1 S multiplied by T2 S. Right? Since there is series, the output of one is the input of the other, hence you will have this kind of. Yeah? Okay. Okay. Now there may be other things as well. For example, there may be a gear here, and accordingly the theta may change. Yeah, so there may be gearing, and depending on the ratio, gear ratio, you will have the theta value. For example, if the gear ratio is such that one turn of this one is the n turn of the last stage, right? So in that case, n there will be a transfer function of n here. Hence, you have to multiply it by n in that case. Yeah. But what else may be there? There may be in this side. Now you know that given the voltage, how much theta will be. That we know. Now we have to complete the control system. That's what we are doing it. Okay. So how to control? So we may look it as one example where we are trying to show the control system how it works. Okay. Let's take example of a servo motor. Yeah? So a servo motor, you have to control basically. You have to tell that say there is a knob here, yeah, and you want this to move to a particular angle. So this is input, right? Okay. So how it will be? So let us say you are starting with this is 0 angle, and you want to move it to different angle, right? So let us say from here to here, and you have 90 degree, 180 degree, let us say, yeah, this is 0 degree, and so on. And so basically there is a knob here, you are turning it, and you want the motor to move that way, right? To go like move. So what do we want? We want finally the load to move by certain amount, like in robotic system, right? So you want, or maybe anything like remotely you want to do something. You want to, from here you want to move something by some angle. So this is what you are in your hand, you are turning the knob. Let us say you want to move by 45 degrees. So accordingly you will move here, and you want the load here, this theta also moves by that 45 degree. For doing that, of course, what you will do, you will have a kind of potentiometer here. So say this is a resistance like this one, right? Okay. So this is a potentiometer. So it input potentiometer. Yeah. Okay, and you will have one side. Okay, sorry. So this will be at, say, grounded, and this side you have some voltage there, right? So plus some voltage, Yeah. So this is what this is going, you are going to get some voltage from here, because it's a potentiometer, you are going to get some voltage from here, right? From here like this. Now this voltage, let us say this one is potentiometer, say EP is the potentiometer voltage. Yeah, with respect to, of course, the ground. Now there will be at the output also, you have to know what is the state there, means what is the, at what location the load is right now. Yeah, so that means that this one is your what you intend to do, but what actually it is here. So you have to measure it. Hence there will be a sensor, right? There will be a sensor. A sensor is going to get some, so this is a sensor, right? So sensor will be here. So sensor is coming here like this. Yeah? This is going to sense what the theta is. Sensor could be in terms of, there also there may be potentiometer there also, right? So since the, like you have a motor here, the shaft here, and at the shaft or you have the load there, the flywheel there. On the flywheel itself, there may be a potentiometer, something like this one, and from there you can find out what is the angle there. Yeah, so the angle could be something else, right? Angle may, here you want 45, but here it could be 50 degree or could be 30 degree. So the state from there you have to find out. Yeah, so here also there will be similar thing. Yeah, and what we're going to do is this, we have to, this is the sensor, and this will be installed where? This will be installed somewhere here on the shaft itself, so that you know the position of the shaft, and that position of the shaft will come as the, we call it ES, right? Sensor, E for sensor, ES for sensor. Yeah, so this is ES, right? So this will is the sensor which senses that ES, right? And so basically that really means there will be here K, which is about a feedback loop, so let's call it KF, and here you have ES. So ES is not here, but this is the sensor. So this is the sensor. So input is theta S, right? And the output is the ESS. S for sensor. Yeah, so we are taking the Laplace transform already. Yeah, so sensor has the gain also, like a constant, such that ES S is equal to KF times theta S. So this is measuring. So basically the theta is the physical quantity, the mechanical quantity, and finally we have to convert into a voltage, right? So that we can play with it, right? So that we can control it, because here the input is here is voltage only. Hence we have to, the sensor, what the sensor will do, sensor will just sense where the position is, and that position will be converted into the voltage. And how? This is the mechanism how you will convert it, right? So on the flywheel, let us say this is a flywheel, on that there will be a potentiometer like this one attached, and depending on where it is, it will convert that into a potential ES, right? So and hence this is a transformation factor, right? So this K multiplied with theta S will give us the voltage, which is actual. this is the desired, EP is the desired one, right? The potentiometer. So so this is E for potentiometer, input potentiometer. So this is the, we can also say EI, let's call EI, I for input, right? EI. And this is what here S for the sensor. So now from here we are getting the ES part, right? So this is ES. So we will take the EI part. So we have taken the Laplace transform of that. So we have here this is the desired one. So this is also desired, and this one is the actual. Yeah. So what we're going to do, we are going to add it here. Okay. So like this one, we say like this. Yeah. So this is going to plus, and typically what is done, this is called a feedback loop. So this will go to here. Yeah. So minus. Typically this will be a minus. Why minus here? This has to be subtracted from the original one. Why? So that we get the error basically. Yeah, typically we have the error part there. But before we have the error, after we sum it up, there may be a gain as well. So what I mean is, we will move a little bit this side. This another gain, let's call K1, okay, and then so this is the error. So this is this is the error ES, EE we can call it, and then we have like this. This is minus, so this will go to this one, and here this is plus, so here go like this. Yeah. Okay. So this is how the connection is. Yeah. So let me explain again. Okay. So we have completed that. So this is input potentiometer. This is what we want, right? This is what we want. So the voltage will tell us this is the angle we want, 0 degree, let's say 45 degree I want. So I want 45 degree, I move it by 45 degree, and because of potentiometer, what is going to do? It is going to convert that 45 degree into the voltage, and this is what the input is, right? So here our input is EIS. Okay. This is the output, the actual position of the shaft now. Yeah. And this also has to be converted into a voltage, corresponding voltage. And what it does, you do through a sensor. A sensor could be on the flywheel itself, there may be some potentiometer, and because of that we can actually find out, convert that into a voltage, and that will give us the position. So we are measuring it theta by a sensor. This is the sensor. Okay, and converting into corresponding voltage, and we are going to subtract here. So this is a, what you call it, summing point, right? This one is summing point, and this is called branch point, right? Branching point, right? And this is called feedback. This is called feedback loop, and this is what makes it a closed loop system. Yeah, this is closed loop system. Yeah. If we do not have the sensor here, then it will be open loop system. So open loop. Yeah. Open loop without feedback. That is without feedback. Yeah. Okay. So how it works basically? So here, let us say the original, the state right now is 35 degree. You want 45 degree. Hence you will see that there will be change in this and this will be exactly the same, so that if here 45 degree and here 45 degree, you get exactly the same voltage from both of them. And then if you add them, since this is going to subtracted, this will be going to subtracted from this one. Hence you have plus here and minus here. Then it will be 0. If both the position, desired position and the actual position are the same, total voltage will be 0. Hence if you give here 0 input here, and hence output will be 0. Input 0 for this one, output will be 0. And similarly, what happens is 0 input here, so output will be 0, and hence it will remain where it is. Since there is no input at all, in that case it will remain where it is. Now if there is a change, let us say, now this is at 35 degree and you want 45 degree. Now this is at 35 degree. That really means that this one will, whatever voltage it will give you, or whatever voltage give you, there will be a difference. Here the voltage in this case, the input desired one will be more. More than this minus this is a positive number. Hence there will be a value here. This will derive value this one. This will also have, and if there is a value here, there is a current. There will be voltage here. Hence the motor will run. When motor runs, there will be a torque generated. If the torque generated, the theta will change. Okay, and as soon as this reaches value close to the desired value, it is going to stop. So it will go in a stepwise. So now if it is let us say at 55 degree and you want 45 degree, then what happens? This will have higher voltage. This will have a lower voltage. So net will be minus. So your voltage what you are going to give will be negative voltage. So magnified negative voltage. Because of that, the motor will run backward, right? So backward meaning the clockwise. And if it work clockwise, the torque will be negative. Hence, it produces negative theta. Hence, it will correct it. It will bring it to 45 degree desired, right? So this is how it works. So today the idea was to show things. How it works. Only thing what remains now is find out what is the total the transfer function. Yeah. So transfer function here, I will remove the potentiometer part because those are just for explaining purpose. Yeah. And what we have is the system is something like this one. Yeah. Okay. So our system is like this one. Yeah. So let's correct it a bit so that it looks good basically. So here typically we write it like have all straight like this one. Yeah. And here you have input. Yeah. These are summing points, so we can also write this is the like this. So instead of showing the desired voltage this side, I am showing from that side. So this is plus, this is minus, and this is input, EIS. So EIS is the input, this is the input, right? And the summing point, the feedback coming like this one. And now we have to find out, if somebody tells you find out the open loop transfer function. Open loop transfer function. So then what you do? You remove this one. This one is removed. So what we will do? Remove it, right? Remove this one. Okay, and then we get T open loop. Let's call it TO open loop. Yeah, and then what we will do? For open loop, we have simply this K1. We just multiply all of them and we will get it. So K1, right? So basically, why multiply? Because this will be equal to what? We will be equal to theta S divided by EIS, right? EIS. That's what it is. And this will be equal to theta S divided by tau S, then tau S divided by EAS, and then EAS, divided by EES, right? This is the error here. This is the error, right? This error, or steady state error is called. So this is the EAS, right? Like this one, and in this case, since there is a in the open loop, EIS and EES will be the same, because whatever coming here, it is going there, right? Equal multiplied by EES divided by EIS, right? And hence, what you get? The first one, theta s over tau s, theta s over tau s, simply 1 over JS square plus BS. Then this tau s over EAS. So then whatever value this one is, you have KA JS plus B divided by LAS plus RA JS plus B plus KA times KB, that you get. Yeah, and then EAS over EES, EAS, EES. So this is just to error has to magnify it, just to amplify it. You have this scale, right? So multiplied by KA, right? So this is what the open loop transfer function. Yeah. Okay. If somebody asks you, okay, what is the closed loop transfer function? This is open loop, the closed loop. Then in closed loop, you have to do some analysis. Okay. What is the analysis? Okay. So now closed loop. So just see here like this one. So closed loop. So this is the open loop one, right? And then you have to find out the closed loop one. So here, what you see here, EES is nothing but EIS minus ESS, right? So this is what this one is, okay? Is equal to, now ES is equal to this one, so EIS minus ESS is nothing but KF, this is the feedback, KF times theta S, right? Okay. Now we have the this is input, right? And then this one is okay. This is the error, like this one. Okay. Now from we know that from here to theta s, so ES is nothing but open loop transfer function multiplied by the theta s will be this one is open loop transfer function. Open loop transfer function multiplied by this one is theta s. That is the thing, right? So we can write like this. So we have theta s. We have theta s multiplied by theta s over EES is equal to original is the open loop transfer function T naught S, right? And hence we get theta S or EA or EES. So EES equal to theta S divided by T naught S, right? So we can write it here. So same thing we write it here. We get theta S over T naught S will be this one is equal to EIS minus KF theta S. Okay. Okay. Now we bring it here, and then what do we get? So we get 1 over T naught S plus Kf, right? So 1 over T naught S plus Kf, theta S will be EIS, and this will give us the closed loop transfer function Ts equal to, which will be equal to theta S, sorry, theta S divided by EIS, right? So theta S divided by EIS will be equal to, theta EIS will be 1 over, okay, so this will be 1 over theta S, 1 over T naught S plus Kf, right? Or simply here I'm going to write the final value, or simply what you get, closed loop transfer function will be equal to, if you see here, between open loop transfer function divided by 1 plus Kf times open loop transfer function. So open loop transfer function we all find out. You remove this feedback loop, yeah, and you find out what is the open loop transfer function, and then once you know that, then closed loop you can find out from there. So closed loop transfer function equal to open loop transfer function divided by 1 plus Kf, Kf is here, multiplied by open loop transfer function. So you can find out easily from there, yeah. So see here, this is negative, so you also call it negative feedback loop, yeah. So this is what it is, yeah. So open loop also output over input here, yeah, but this is not there, so this EI equal to EE only becomes, and hence this is the T naught S you get, and closed loop you get theta S divided by EI, and that you get T naught divided by 1 plus Kf times T naught, where T naught is the open loop transfer function. So this is what the takeaway.